Are these cannons prepped for transport?
Almost, sir. We're still waiting on the firing pins.
They were supposed to be here yesterday. This is unacceptable.
Did they brief you on the new protocols?
Only that it's urgent and highly classified.
We must be careful what we say, even here.
January 1941. A bitter wind cut across the quiet fields outside Wilmington, Delaware. Smoke curled from the stacks of the DuPont chemical plant, the acrid scent of nitrates and solvents stinging the air. Inside, engineers hunched over steel tables, pencils scratching formulas on yellowed paper, eyes darting nervously between chemical diagrams, and the clock ticking toward the next test. In the artillery depots across the country, wooden crates sat empty. Cannons, polished and ready, pointed toward invisible targets, but there were no high-explosive shells to fire. The U.S. Army stockpiles were dangerously low, the threat of global war pressing on every mind. Military officers paced the concrete floors, checking lists, muttering to one another, aware that every delay could cost lives on distant battlefields. At DuPont, chemists ignited small test charges, measuring blast patterns with meticulous precision. Each failure sent shivers through the lab. A misfire, a crack, an unstable mixture, and the looming question remained: could America arm itself in time? Could these men, in white coats and protective goggles, invent explosives that would match the deadly efficiency of war already raging overseas? The race had begun. The nation's artillery and its honor hung in the balance. By January 1941, the world had already been engulfed in war for over a year and a half. Europe was in flames. Germany's blitzkrieg had conquered Poland, Denmark, Norway, Belgium, the Netherlands, and France. Britain stood alone against the Axis onslaught, its cities shadowed by the constant threat of Luftwaffe bombing. Across the Atlantic, the United States remained officially neutral, but neutrality did not mean inaction. Washington's leaders watched the unfolding devastation with mounting concern, knowing that sooner or later, America would be drawn into the conflict. The U.S. military, however, was not ready. Its artillery corps faced a glaring deficiency, a shortage of high-explosive shells. Existing stockpiles, remnants of interwar budgets, and limited production runs were insufficient to arm the nation's cannons. Reports from Army depots painted a stark picture. Crates sat empty, and frontline units training on domestic ranges often found themselves unable to conduct realistic live-fire exercises. The problem was not merely logistical, it was existential. Artillery had become the backbone of modern warfare, determining the fate of battles, the survival of infantry, and the destruction of enemy fortifications. Without these shells, America's guns were effectively silent, its deterrent hollow. Pressure came from multiple directions. Britain, struggling to resist German advances in North Africa and preparing for a possible invasion, urgently requested military aid through Lend-Lease. The U.S. War Department, under Secretary Henry Stimson and Chief of Ordnance General Brian Somervell, scrambled to meet these demands. Yet the nation's industrial base was still in peacetime rhythm. Factories produced consumer goods as much as military hardware. Steel was allocated carefully. Chemical plants operated on schedules optimized for efficiency, not wartime urgency. And the chemistry behind high-explosive shells was far from simple. Not every explosive could withstand the shock of firing, survive the barrel, and detonate reliably upon impact. A single miscalculation could result in catastrophic failure, disastrous not only for artillery crews but for the nation's credibility. DuPont, the chemical giant headquartered in Wilmington, Delaware, emerged as America's most capable and most pressured partner. Founded in 1802 as a gunpowder manufacturer, the company had evolved into a technological powerhouse, producing chemicals, plastics, and explosives. Its laboratories housed some of the brightest chemists and engineers in the country. Yet the challenge before them was unprecedented. They were not simply producing more gunpowder. They had to innovate. Standard formulations for TNT and other explosives existed, but they were designed for older munitions. Modern artillery demanded new blends that combined stability with maximum destructive force. The stakes could not have been higher. Military planners in Washington calculated that even a single month's delay in production could leave American forces and their allies vulnerable. Intelligence reports hinted at Germany's increasing artillery range and precision, while Japanese expansion in Asia threatened to destabilize the Pacific. Every empty crate, every failed test, represented a gap that the enemy could exploit. Engineers worked in shifts, laboratories humming with electricity and chemical reactions. They measured velocity, density, and detonation pressure with painstaking precision. Every spark, every misstep carried a human cost. Yet amid the tension, there was determination. DuPont's leadership coordinated directly with the Army's Ordnance Department, sharing formulas, testing protocols, and production timetables. Communication was constant. Telegrams and memos flew faster than any train. Chemists experimented with new combinations of nitroglycerin, TNT, and other compounds, adjusting ratios by the gram to achieve the perfect balance of power and safety. Safety itself was a constant concern. Explosives were unforgiving, and accidents could be fatal. Even minor miscalculations in temperature, moisture, or pressure could set off a catastrophic chain reaction. This was not a war fought on the battlefield, at least not yet. It was a war fought in laboratories, factories, and offices. The enemy was distant, but the threat was immediate. DuPont's engineers understood that success meant more than technical achievement. It meant giving America and its allies the tools to survive the storm already sweeping across continents. Each test charge that detonated successfully was a small victory, proof that science could respond to urgency, that innovation could overcome scarcity. As January turned to February, the pressure intensified. Orders piled up, depots remained half empty, and Washington demanded results. The situation was fragile, and yet the potential for breakthrough was real. The stage was set for DuPont to confront not just a technical problem, but the very demands of modern war itself. The nation's artillery and its honor depended on the next formulation, the next successful test, the next spark in a laboratory far from the front lines. The tension of these months laid the foundation for the angles that would shape this story. Human courage, technological ingenuity, tactical necessity, and leadership under pressure. By early 1941, DuPont's laboratories had become the nerve center of America's high-explosive development effort. Engineers and chemists worked under relentless pressure, often 16-hour days, surrounded by stacks of reference manuals, chemical samples, and intricate blueprints of artillery shells. The challenge was both scientific and practical. The explosive had to survive the violent acceleration inside a cannon, remain stable during transport and storage, and detonate with predictable force on impact. The margin for error was razor thin. Standard formulations like TNT had been used for decades, but the war had exposed their limitations. Early tests revealed that some shells cracked under the extreme pressure of modern cannons, while others failed to detonate reliably. Nitroglycerin, more powerful, was dangerously unstable. Even slight deviations in humidity or temperature could turn a batch into a ticking hazard. DuPont's chemists faced an exacting puzzle: create a mixture that was both powerful and safe, a combination that had eluded conventional approaches. Initial attempts were slow and often disastrous. Small-scale detonations in controlled chambers frequently ended in violent failures, shattered test casings, scorched floors, and charred laboratory benches. Each mishap forced teams back to the drawing board. Calculations had to be redone, ratios adjusted, and even the sequence of chemical mixing reconsidered. One memo from January 1941, preserved in DuPont archives, notes, repeated failures have underscored the volatility of nitro-based formulations under cannon firing stress. New stabilizers must be evaluated immediately. The language is dry, clinical, but the stakes were far from abstract. A miscalculation could destroy both lives and national confidence. Military engineers visited Wilmington frequently, observing tests, taking measurements, and pressing for timelines. The pressure was not simply bureaucratic. The U.S. Army needed artillery-ready shells yesterday. Depots across the country remained critically understocked. Training ranges could not simulate realistic combat conditions without functional shells. Units scheduled to ship overseas faced the uncomfortable reality that their guns were largely ceremonial until DuPont succeeded. Despite the setbacks, innovation emerged. Chemists experimented with a range of additives and stabilizers to prevent premature detonation. They tested alternate binders to reduce the risk of cracking during firing. Each test involved meticulous recording: temperature, humidity, grain size, detonation velocity, and impact effectiveness. It was a laborious process, but every data point brought them closer to a viable solution. By mid-February, small successes began to appear, charges that detonated consistently in the lab, with minimal signs of instability. Each success was celebrated quietly, with notes logged and samples preserved for replication on a larger scale. The scale-up from laboratory to factory production introduced a new set of challenges. Ingredients that behaved predictably in grams sometimes reacted unpredictably in tons. Mixing vats had to be redesigned, temperature controls fine-tuned, and quality checks implemented at every stage. DuPont's leadership coordinated closely with ordnance officers to ensure that any breakthrough in formulation could be rapidly translated into production-ready shells. For the military, time was as critical as chemical precision. Simultaneously, engineers had to consider storage and transportation. High-explosive shells would not remain in a laboratory. They would be shipped across states, sometimes overseas, to depots, training camps, and eventually battlefields. Stability under varied conditions, cold winters, humid summers, long journeys, became as important as performance under firing stress. In practice, this meant repeated testing under simulated conditions, from freezing chambers to heated containers, measuring every batch against rigorous standards. Amid these technical challenges, morale was fragile but determined. Laboratory staff understood the human dimension of their work. Letters from military officers, circulated internally, described the stakes in stark terms. Every delay in shell production meant fewer soldiers trained under realistic conditions, fewer rounds available for allies in desperate need, and potentially more lives lost in combat. DuPont chemists were acutely aware that their work would not stay on the factory floor. It would travel in the bellies of ships, roll into artillery tubes, and explode on foreign battlefields. The responsibility was tangible. By late February, the first small-scale successes hinted at a breakthrough. The formulations had survived cannon trials with minimal cracking. Detonations were more consistent. The technical framework for mass production was in place, though enormous work remained to scale up while maintaining safety and effectiveness. These months of trial, error, and incremental victory laid the foundation for the angles of this story. The human perseverance of engineers, the technological ingenuity in chemistry, the tactical consequences of artillery shortages, and a leadership that coordinated a nationwide response to a growing crisis. The laboratory victories, tentative though they were, set the stage for the coming race, transforming small, controlled tests into mass-produced shells capable of equipping an army on the brink of global war. The world waited outside Wilmington, and inside, the race against time had only just begun. Inside the DuPont laboratories, the war was fought not with rifles or tanks, but with pencil, beaker, and blast chamber. Engineers and chemists worked under relentless pressure, their lives defined by measurements in milligrams and milliseconds. Many were veterans of World War I munitions programs, but even they had never faced a challenge of this scale. The urgency was constant. Each failed detonation, each cracked shell, was a reminder that soldiers' lives depended on their calculations. Fatigue and fear were ever present. Protective goggles and gloves could not shield them from the anxiety of a miscalculation. Yet, there was a quiet camaraderie among these men and women. Small victories, an experimental charge detonating exactly as predicted, were celebrated with subdued nods, whispered congratulations, and meticulous record-keeping. They understood the stakes. A single misfire in a cannon could kill the gun crew, and a single failure in production could compromise the entire artillery campaign. Their work was invisible to the public, yet its consequences would ripple across oceans and battlefields. Letters from military officers circulated in the lab, describing troops training with empty ranges, allies in need of aid, and the specter of a global war that could engulf the United States. These words served as both warning and motivation. The human effort behind every successful shell was immense, a combination of intellect, endurance, and quiet heroism, unrecognized outside the walls of Wilmington. The challenge of creating high-explosive shells was as much chemistry as engineering. Standard TNT, while reliable for decades, could not withstand the pressures of modern artillery. Nitroglycerin offered power, but with terrifying instability. DuPont's chemists had to devise entirely new formulations, combining compounds to achieve both maximum explosive force and complete safety under storage, transport, and firing conditions. Early trials highlighted the complexity. Small variations in moisture content, temperature, or mixing sequence could trigger catastrophic failure. Even the shape of the shell cavity influenced detonation patterns. Engineers invented new test chambers to measure pressure and velocity, while chemists adjusted chemical ratios gram by gram. Data collection was meticulous. Every explosion was documented with photographs, diagrams, and written observations. Each small success informed larger-scale production, but scaling up introduced fresh variables. Ingredients that behaved predictably in the lab sometimes reacted dangerously when produced in tons, requiring redesigns of vats, mixers, and temperature control systems. Innovation extended beyond the chemical mixture itself. The team explored stabilizers to prevent accidental detonation, binders to reduce cracking under stress, and shock-resistant casings to ensure the shell would survive the force of firing. Testing protocols were exhaustive, simulating every imaginable environmental condition, from frigid storage warehouses to humid transport ships. By February 1941, the lab's technological breakthroughs had laid the foundation for mass production, turning theoretical chemistry into practical artillery tools. The absence of reliable high-explosive shells had profound tactical implications. Artillery was the backbone of modern warfare, dictating the outcome of battles by suppressing enemy positions, destroying fortifications, and shaping the battlefield before infantry advanced. Empty depots meant that training exercises were limited and combat readiness remained theoretical. Troops could drill with guns, but without live shells, they could not practice actual targeting, timing, or coordination, skills that could mean the difference between survival and annihilation on the front lines. Military planners were acutely aware that shortages of munitions created strategic vulnerabilities. British forces in North Africa and Europe depended heavily on American production. The Lend-Lease program, which would soon provide critical artillery shells to allies, could not function if the United States itself could not manufacture reliable explosives. Each day that passed without a viable shell was a day in which soldiers faced potential defeats that might have been avoided. The tactical ripple effect extended beyond training. Artillery units poised for deployment, whether to Europe or the Pacific, were effectively immobilized. Commanders had to plan operations around what they lacked rather than what they possessed. Without sufficient high-explosive ordnance, even the best-trained troops faced serious handicaps against enemy forces whose artillery capabilities were already proven and lethal. DuPont's breakthroughs were therefore not academic. They were a direct lifeline to tactical effectiveness, turning theoretical firepower into a force that could shape the battlefield. The human perseverance, technological ingenuity, and tactical necessity converged in Wilmington. Engineers and chemists labored to create a product that would transform empty depots into arsenals, theoretical strategies into actionable plans, and anxious officers into confident commanders. Their work was unseen, yet its impact would soon reach every battlefield where American artillery fired. The DuPont laboratories were more than a chemical workshop. They were a command center of innovation under pressure. Executive leadership played a decisive role in translating laboratory breakthroughs into practical, mass-producible shells. Pierre S. DuPont and the company's senior managers understood that scientific success alone was insufficient. Speed, coordination, and accountability were equally critical. They maintained constant communication with the U.S. Army Ordnance Department, sharing progress reports, chemical data, and production timetables. Decision-making was relentless. When a batch of experimental shells cracked during testing, executives and chemists convened immediately, analyzing whether the failure stemmed from chemical formulation, casting methods, or environmental factors. Priorities were recalibrated hourly, balancing safety with urgency. DuPont leadership also liaised with Washington to ensure that procurement, logistics, and distribution channels were ready to handle the first successful shells. The stakes were enormous. A delayed shipment could compromise Allied operations abroad, while a poorly manufactured shell could injure or kill American soldiers at home. Leadership was thus both technical and moral, guiding men and women through a maze of innovation, risk, and wartime necessity. Across the Atlantic, German forces were already perfecting artillery techniques that would dominate early 1941 battlefields. Blitzkrieg tactics relied on precision bombardments, with high-explosive shells devastating fortified positions in seconds. The Axis powers had refined their chemical engineering to produce stable yet deadly explosives, giving their artillery units unmatched reliability and lethality. For American planners, this enemy capability underscored the urgency. Lagging in high-explosive production would leave U.S. and Allied forces exposed to firepower that could not be matched. In the Pacific, Japanese artillery and coastal defenses presented a different, but equally pressing, threat. Though the United States had yet to enter the war officially, intelligence reports indicated rapid Japanese expansion in China and Southeast Asia, with fortified positions increasingly reliant on heavy ordnance. A shortage of domestically produced high-explosive shells meant that American forces, if deployed, would be at a disadvantage from day one, unable to counter entrenched positions with effective firepower. Understanding the enemy's capabilities was not theoretical. It directly informed DuPont's priorities. Every chemical formulation had to be robust enough to rival, and ideally surpass, Axis munitions in reliability, power, and adaptability. The shortage of high-explosive shells was more than a technical problem. It was a moral and strategic crisis. Military planners knew that soldiers training with empty ranges could not acquire the skills necessary to survive in combat. Allies, particularly Britain, were calling for urgent support, dependent on American manufacturing to sustain resistance against Axis aggression. Every delayed shipment, Every failed test carried ethical weight. Chemists and executives alike understood that their work could indirectly determine who lived and who died in distant battlefields. Strategically, success at DuPont had implications far beyond Wilmington. The Lend-Lease program, which would soon mobilize American industrial power for Allied benefit, relied on the rapid production of reliable munitions. Political leaders in Washington and London both recognized that America's credibility as an arms supplier hinged on overcoming the shortage. Failure would erode confidence, impede alliances, and limit the effectiveness of future operations in Europe and the Pacific. In this context, every ounce of stabilized explosive, every shell that passed testing, became a symbol of national resolve, industrial ingenuity, and ethical responsibility. DuPont's efforts reflected a broader moral imperative to turn chemical knowledge into a weapon of survival for both American soldiers and Allied forces. The convergence of human determination, technological mastery, tactical necessity, and leadership foresight underscored a simple truth. The war could not be won without explosive innovation, and innovation required courage, precision, and relentless focus. These angles, the human, technological, tactical, leadership, enemy, and moral, paint a complex picture of the crisis in early 1941. Each perspective underscores why DuPont's work was not merely industrial, but existential. The stage was now set for the next phase, the climax, when months of testing, calculation, and labor culminated in breakthroughs that would finally arm America's artillery and transform a nation's role in global conflict. March 1941. Wilmington's skies were gray, the chill of early spring seeping through the laboratory windows. Inside, the DuPont test chamber hummed with an uneasy tension. Engineers lined up small-scale shells, each meticulously labeled, each representing weeks of trial, error, and revision. Outside the lab, artillery depots remained partially empty. Soldiers trained on dry ranges, their cannons poised but silent, awaiting a solution that had eluded the nation for months. The first full-scale test was scheduled for mid-morning. The artillery crew had transported prototype shells to a remote range under strict supervision. DuPont chemists accompanied them, wearing goggles and protective coats, each carrying a clipboard dense with calculations. The shells were loaded into a 155mm howitzer, a weapon designed to hurl explosives over a mile, and the firing sequence began. Hearts pounded as the firing officer counted down. 3, 2, 1, fire. The recoil rocked the gun, sending vibrations through the ground. For a tense second, nothing happened. Then, a controlled explosion erupted at the target, sending a plume of earth and smoke into the air. It was perfect. The shell had survived the cannon's pressure, detonated as expected, and demonstrated both stability and power. Engineers exchanged cautious glances, the first signs of relief flickering across tired faces. But this was only the beginning. Over the next days, the test program expanded. Each shell was fired under varying conditions, colder temperatures, higher humidity, and different barrel lengths. Failures still occurred. A cracked casing here, a delayed detonation there. But incremental successes began to dominate. Every successful firing reinforced a growing confidence. The chemical formulations that had seemed theoretical only weeks earlier were now proving themselves under the brutal realities of artillery deployment. At DuPont headquarters, leadership coordinated the scaling-up process. Production lines were adapted to replicate laboratory precision on a mass scale. Ingredients that had been weighed in grams were now measured in tons. Temperature-controlled mixers were constructed, and quality control protocols were instituted at every stage. Engineers traveled between Wilmington and production plants, overseeing every step, ensuring that the delicate chemical balance was preserved. A single misstep could undo weeks of progress, or worse, trigger an explosion capable of catastrophic loss. The pressure from Washington was relentless. Telegrams from the Army Ordnance Department demanded progress updates, production forecasts, and assurance that the shells would be ready for shipment to Lend-Lease depots within weeks. Officers emphasized that Allied forces depended on these munitions. Britain, engaged in North Africa and preparing for potential invasion, needed artillery support immediately. DuPont's success was no longer confined to laboratory prestige. It carried geopolitical weight. By late March, a series of final, large-scale tests confirmed the breakthrough. Multiple shells fired consecutively, under conditions replicating storage, transport, and battlefield firing, demonstrated remarkable consistency. The formulations were stable, the detonation reliable, and the destructive force met military specifications. Engineers documented every explosion with photographs, notes, and diagrams, ensuring that the knowledge could be reproduced at scale. The human toll of this breakthrough was evident. Engineers, exhausted and often on edge from months of testing and near misses, allowed themselves small celebrations. Quiet smiles, pats on the back, and muted congratulations. The tension that had defined Wilmington for months was giving way to cautious optimism. But the breakthrough was not just technical. It was a validation of human endurance, leadership foresight, and the disciplined orchestration of a complex industrial and military partnership. Meanwhile, military observers began coordinating the next step: deployment. The shells would be shipped to training depots, then to active artillery units preparing for overseas operations. The transition from lab to battlefield was imminent. The success at Wilmington demonstrated that science and industry could respond to urgent military needs, a critical lesson as America edged closer to global conflict. This first phase of the climax, the controlled success under testing conditions, represented the turning point in America's high-explosive crisis. Months of uncertainty, risk, and painstaking labor had converged into a tangible result. Yet the next challenge loomed: mass production and integration into active artillery units. Could DuPont and the Army ensure that these shells would function reliably under the chaos of real warfare? The answer would unfold in the next stage of the story, where the breakthrough moved from laboratory validation to operational reality, reshaping America's artillery readiness and its capacity to support allies across multiple theaters of war. April 1941. The first production convoys rolled out from DuPont-controlled plants under military escort. Flatbed trucks carried freshly sealed crates stamped with stenciled markings: caliber, lot number, date of manufacture. Inside, the new high-explosive shells rested in straw-lined compartments, inert for now, but built to awaken with devastating force. For the first time in months, America's artillery pipeline was moving again. At receiving depots, Army ordnance officers inspected each shipment with surgical attention. Random shells were selected, weighed, X-rayed, and disassembled. The new formulations passed inspection. No seepage, no hairline fractures, no instability. Field reports sent back to Wilmington were brief and precise. Meets specification. Approved for distribution. Training ranges that had remained quiet since the interwar years came alive. Artillery units began live-fire drills using the new shells, observing real blast effects for the first time. Gunners adjusted elevation and timing. Forward observers learned to read smoke patterns and fragmentation spread. The guns finally behaved as weapons, not placeholders. The psychological shift was immediate. Crews no longer trained in abstraction. They trained in reality. As production accelerated, DuPont coordinated output across multiple facilities. The chemical formulation was now standardized, but execution remained unforgiving. Each plant followed identical temperature thresholds, mixing sequences and curing times. Safety officers monitored every shift. Even success was dangerous. Explosives did not forgive complacency. A single shortcut could undo everything. By late spring, shipments began flowing not only to U.S. training depots, but to overseas stockpiles under the Lend-Lease program. Britain received its first consignments of American-produced high-explosive artillery shells shortly thereafter. For British gunners, long accustomed to rationed fire and limited reserves, the arrival of fresh heat ammunition represented more than material relief. It was strategic reinforcement. Washington took notice. Reports reached senior leadership confirming that the artillery bottleneck had been broken. The Army Ordnance Department revised its readiness assessments upward. War planners recalculated operational possibilities. What had once been a glaring vulnerability was now becoming a strength. Behind the scenes, DuPont engineers continued refining processes. Even as shells moved into the field, laboratory teams monitored performance data, studying fragmentation patterns, detonation reliability, and storage durability. Feedback loops were constant. The formulation was no longer experimental, but improvement never stopped. The significance of this moment was not dramatic in the traditional sense. There was no single explosion that marked victory, no public announcement, no parade. Instead, the turning point was measured in tonnage shipped, tests passed, and artillery units finally equipped to fight a modern war. By mid-1941, America no longer faced an he-shell crisis. It faced something else entirely, the responsibility of industrial scale. Production targets rose sharply. What had been a desperate scramble became a disciplined flow of materials, knowledge, and firepower. When the United States would eventually enter the war later that year, its artillery would not enter silent. The crisis that began with empty crates and failed detonations had been resolved not by luck, but by method, by chemistry refined under pressure, leadership willing to accept risk, and human endurance stretched to its limits. As summer approached, artillery shells moved steadily toward ports, training grounds, and future battlefields. The laboratories at Wilmington returned to a steadier rhythm. The emergency phase was over. The consequences were only beginning, and with the guns now armed, the story turned toward what followed. How this breakthrough reshaped production, strategy, and the balance of power in a world already at war. By June 1941, the first full months of production had transformed the U.S. artillery landscape. Crates of high-explosive shells, once conspicuously absent from depots, now filled warehouses across the country. The empty training ranges were alive with thunderous fire. Cannons that had stood idle for months now hurled shells across miles of terrain, creating smoke plumes that marked both success and readiness. Soldiers could train under realistic conditions, adjusting fire, learning trajectory corrections, and mastering the rhythm of artillery coordination. Production numbers were staggering. Wilmington and satellite plants were churning out thousands of shells weekly, each meticulously tested and cataloged. The Army Ordnance Department kept detailed records of lot numbers, chemical compositions, and firing results. By midsummer, reports indicated that artillery units in training camps could finally sustain exercises without interruption, a stark contrast to the early months of 1941, when empty depots had left gunners rehearsing motions rather than actual firing. Across the Atlantic, the impact on Allied forces was immediate. Britain, heavily engaged in North Africa and preparing for the defense of Malta, began receiving U.S.-produced shells through the Lend-Lease program. These shipments arrived at crucial moments. British artillery, often stretched thin, now had reliable munitions for both training and combat operations. War diaries from the Royal Artillery note the importance of American support, highlighting how the consistent supply of shells allowed units to maintain continuous firing drills and prepare for offensive operations that had previously been constrained by shortages. The human element of this aftermath was equally striking. Engineers and chemists who had labored under relentless pressure witnessed their efforts transforming into tangible results. There were no parades or medals, but a quiet satisfaction permeated Wilmington. Letters from Army officers thanked the teams for their dedication. Memoirs written later describe the tense months leading up to March as a period of near-heroic persistence, with every minor victory, successful detonation, stable batch, smooth production run, contributing to the eventual triumph. Strategically, the availability of high-explosive shells had broader implications. U.S. military planners could now consider forward deployments with realistic confidence in artillery support. Training regimens improved dramatically, ensuring that soldiers heading to overseas theaters would be well-versed in live-fire operations. The confidence of commanders increased. Where uncertainty had once dictated cautious planning, the new ammunition supply allowed for operational flexibility. Industrial coordination became a model for wartime production. DuPont's management refined logistics to balance laboratory innovation with mass output. Quality control remained rigorous. Each shipment, no matter how large, was subjected to testing protocols to prevent defective rounds from reaching the field. This combination of precision engineering and large-scale manufacturing demonstrated that American industry could meet the demands of modern warfare, a lesson that would reverberate throughout the country as mobilization intensified later in 1941. Yet, even as successes mounted, challenges remained. The growing supply chain introduced potential vulnerabilities, transportation delays, storage issues, and a need for continued innovation under pressure. The Army and DuPont had to maintain rigorous oversight, ensuring that every shell reaching depots, training grounds, or Allied hands met the highest standards. Failures were no longer acceptable. The stakes were now global, with the eyes of both allies and enemies watching. The months following the Wilmington breakthrough marked a turning point not only for American artillery, but also for industrial military cooperation. The crisis that had begun with empty crates and failed laboratory tests had been resolved through innovation, persistence, and precise execution. The artillery units, now armed and trained, were poised to enter a war that was already reshaping the world. The human, technological, and strategic investments made in those cold winter months had yielded results that would echo across battlefields, training ranges, and Allied planning rooms alike. As the first wave of mass-produced shells reached their destinations, the nation shifted from urgency to operational confidence. The immediate threat of unarmed artillery had passed, but the long-term impact of DuPont's work was only beginning to be felt, a transformation that would shape not only the outcome of upcoming battles, but also the broader trajectory of American war production. This period of rapid production and deployment sets the stage for the next section. The full strategic consequences of the breakthrough, including the broader wartime impact and the lessons learned in both industrial coordination and military readiness. By late 1941, the DuPont breakthrough had reshaped the American artillery landscape and influenced the broader trajectory of the war. Production lines were operating at full capacity, supplying not only domestic training ranges, but also supporting Allied forces across multiple theaters. The reliability of these high-explosive shells allowed the United States to move from a position of preparation to one of tangible strategic influence, even before formally entering the conflict. The impact on military readiness was profound. Units equipped with the new shells could train rigorously, coordinating artillery barges with infantry maneuvers, refining fire control techniques, and practicing long-range targeting. The confidence of gunners, often wary due to prior shortages, increased significantly. Commanders could now plan operations knowing that the backbone of modern warfare, the artillery, was functional, consistent, and reliable. Exercises that had once been constrained by ration shells now proceeded without interruption, producing soldiers trained under conditions that closely mirrored combat realities. Allied operations benefited immediately. Britain, still engaged against German forces in North Africa, relied on Lend-Lease shipments of American-produced shells to sustain their campaigns. Units that had previously faced limited firing opportunities could now engage in continuous bombardment exercises, refine targeting strategies, and prepare for offensive operations that had previously been delayed by ammunition scarcity. Letters from the Royal Artillery at the time acknowledged the critical role of American munitions, emphasizing that even before U.S. combat involvement, the reliability of these shells contributed directly to operational successes. Strategically, the DuPont effort demonstrated the power of coordinated industrial military action. Laboratories, factories, and ordnance offices operated as a single, interconnected system. Lessons learned in Wilmington: rigorous quality control, meticulous documentation, and the rapid translation of laboratory success into production became a model for subsequent wartime manufacturing. The process showed that technological innovation alone was insufficient. It had to be matched by leadership, logistics, and disciplined execution to achieve impact on a national and global scale. The psychological effect was equally significant. The knowledge that American artillery could now reliably deliver destructive force instilled confidence in both military planners and political leaders. It reassured soldiers and commanders that preparation was no longer abstract, and it signaled to allies that American industry could meet the challenges of modern warfare. For DuPont employees, the achievement reinforced the human dimension of the effort. Months of toil, danger, and calculation had translated into lives potentially saved and battles made possible. Numbers tell part of the story. By the summer of 1941, production had reached thousands of shells per week, with every batch passing strict safety and performance standards. Depots that had once been empty were now stocked and ready. Forward-deployed artillery units received sufficient supplies for extended training and combat operations. The scale of this achievement cannot be understated. In a nation still mobilizing, the transition from scarcity to abundance in a matter of months represented a logistical and technological triumph. The breakthrough also had lasting consequences for American wartime strategy. Reliable, high-explosive shells became a cornerstone of artillery doctrine, influencing tactical planning, force allocation, and joint operations with Allied forces. Military exercises could now replicate battlefield conditions more accurately, preparing troops for engagements across Europe, North Africa, and eventually the Pacific. The trust in munitions shaped operational confidence, allowing planners to coordinate large-scale offensives that would later define U.S. involvement in World War II. At a human level, the aftermath reflected the interplay of science, leadership, and perseverance. Engineers and chemists who had worked tirelessly under immense pressure had validated their expertise. Military officers who had once fretted over empty depots could now plan with certainty. The success at Wilmington exemplified the marriage of intellectual rigor and industrial capacity, a combination that would become a defining feature of American wartime production. In sum, the crisis that began with empty crates, failed laboratory tests, and anxious officers had been resolved through innovation, collaboration, and relentless determination. The immediate tactical benefits: ready artillery units, trained soldiers, and supportive Allied forces were profound. The long-term strategic consequences: industrial coordination, operational confidence, and the establishment of reliable munitions pipelines would reverberate throughout the war. With artillery now armed and production stabilized, the nation could reflect on what this breakthrough represented, not just in material terms, but in human, technological, and strategic achievement. It set the stage for the final, reflective section, where the broader meaning of this crisis and solution would be considered in the context of history, industry, and the human spirit. The story of America's high-explosive shell crisis in 1941 is not a tale of battlefield heroics or dramatic combat. It is a story of human ingenuity under pressure, of quiet determination in the face of global uncertainty. In Wilmington, Delaware, chemists and engineers worked in white coats, far from the roar of artillery, yet their impact would echo across continents. Each careful measurement, each cautious test, represented a small but essential victory, a victory that would ensure soldiers, allies, and ultimately the nation could fight effectively when the time came. Innovation in this story was inseparable from urgency. DuPont's breakthroughs were not merely technical. They were moral and strategic acts. By transforming chemical knowledge into reliable munitions, the company enabled the U.S. Army to train, to plan, and to project power even before formal entry into the war. It demonstrated the power of industrial coordination, leadership, and meticulous execution, proving that human effort could bridge the gap between scarcity and survival. There is a lesson in the quiet tension of those Wilmington laboratories. Modern warfare is not only fought with guns and tanks, but with ideas, precision, and resilience. The empty crates of January became the stocked depots of summer through persistence, calculation, and collaboration. And in doing so, they set a precedent for American industry's role in the global conflict, a model of ingenuity, adaptability, and responsibility. As history would show, the first shots of American artillery fired in anger were supported by months of preparation in labs far from the front lines. The DuPont engineers' work stands as a testament to the unseen human effort that underpins every battle, every campaign, and every strategic decision. It reminds us that innovation in war is not always measured by explosions alone, but by the lives it preserves, the allies it supports, and the confidence it instills in those who bear arms. In the end, the story of high-explosive shells in 1941 is a story of preparation meeting necessity, of science meeting strategy, and of a nation quietly arming itself for the immense trials that lay ahead.